is called the objective function. So there it is. Okay, let's actually see if we can come up with this, all right? Let's come up with it. And I will erase this. And I want to leave these up here because I'm going to need them. Okay, what will the cost of this project be? The cost will be equal to what? Just in real basic like words, tell me what it is. The cost of building the chain plus the cost of building the wood, right? I mean, that's what the cost of this is going to be. So this is the cost of the chain link fence plus the cost of the wood part of the fence. If I can get those two added up together, then I'd have the cost, right? Now, how much is it going to cost me to build the chain? $5 per foot, right? But I don't know the dimensions of this yet. That's actually what I need to figure out. I need the dimensions of this. But we do have some information. We know that the dimensions have to follow this rule that the area, right? Each pen must be 20 square feet. So let's start assigning some variables, because right now we're going to allow this pen to like move, change, and we're going to try and nail down exactly the lowest cost pen. So why don't we call this distance from here to here y? Is that okay? Yes? And why don't we call the width of one of these pens x? If we do that, we can actually put some numbers to these now, at least some variables to them. The cost of building the chain link fence is $5 times each foot we have. Well, how many feet of blue fence are we going to have? We're going to have x plus another x plus another x plus another x. So how many x's up here? 4 of them. Here, another 4 x's. And here, 3 y's. Understand? So this is going to look like this. $5 times 8 x's plus 3 y's. That will be how much we will pay for the blue fencing. $5 times every foot. We have 8 of these x's, and we had 3 of those y's. Make sense? Okay, how much is the cost of the wood? Well, it's $9 times however long we need, or the length we need for the wood, which is this section and this section, which is only 2 y's, right? And I can actually distribute, and I have something here. It's not a function, but it is something. This is 40x plus 15y plus 18y. So this gives me 40x plus 33y. Agreed? Okay, so I needed a cost function, right? I needed a cost function. Here's what I have so far. The cost of building this fence will be 40 x's plus 33 y's. Now, in my wording here, in the beginning I said, I need a function, right? When we say function, we mean a function of a single variable. Like everything we've done, everything we've graphed, we found max and mins of, have always been like f of x equals something, and it's just x's in there, right? Right now, our function has 2 variables in it. And we don't have a way of dealing with this. We have never looked at functions of 2 variables. You take Cal 3, you do that. You do multiple variable. It's called multiple variable calculus because you have more than one variable. So we can't deal with this right now. All right? There's something we haven't used, though. There's a piece of information in here we haven't used. The 20 square feet. I can't just like arbitrarily build this thing. I have to have each of these be 20 square feet. So let's write that idea down as a math like mathematically, what does it mean? This piece right here. What does that mean mathematically? The square footage of the entire thing is 80, right? I agree. But I'm looking for something else. It's along the same line. X times y equals 20. Do y'all agree with this? Okay, so when we look at our picture, if I know that this thing right here has to be 20, and I call that y and I call that x, then when I multiply x times y, it better be 20, right? This right here is what we're going to use to finish this out. This has a very special name to it. This is called the constraint equation. So we were trying to find our objective function, right? We set out to find our objective function. We kind of assigned some variables. We came up with a cost function. Our cost function had two variables in it, so we were kind of like, crap, what do we do? Then we realized there's a piece of information that we haven't used that creates this constraint on the x and the y. You can't just let x and y be anything you want. They have to multiply to be 20, right? So what I'm going to do now is I'm going to take that constraint equation and I'm just going to solve it for y real quick. That means y is 20 over x. Agreed? And then I'm going to come back over here to my cost equation and I'm going to replace the y with that. Because that is what y has to be, right? So I come back over here to my objective. I rewrite 40x plus 33 times y, but y is 20 over x. And now what we have is a final version of our cost function, right? I'm going to just clean that up. Now watch what I do here. What is that, 660? Notice I didn't write c, I wrote c of x. Because I want to make sure you all understand what we've done is we've taken an equation where you had cost was dependent upon two variables, and we've rewritten it so that the cost depends on one variable. And since the cost depends on one variable, we can treat the cost as a function of that variable, as a function of x. And so now this should start to now look more like what we've been doing. The idea is, can you find the maximum, or sorry, no, the minimum, right, of this function? Can you find the minimum of this? Are there any domain constraints here? Are there any restrictions on x? X can't be 0, right? It's got to be positive, because if you hire a company and we're gonna put -8 feet of fence, right? That's when you fire them, right away. So in the real world, like in terms of the algebraic function, you can have negative x's. But in terms of the problem it's coming from, your domain is restricted, right? So what I'm going to say here is that my x has to be bigger than 0, right? And is there any bound as to how big it can be? 20? I could make this, look at this one pen right here. Couldn't I make it 40 feet long and half a foot deep? Wouldn't that still have an area of 20? Now, of course, the animal, I'm putting baby chickies in here. They're like this big. So you don't know what I'm putting in here. Half a foot's plenty of room for these guys. Right? Yeah, right? So really, there is no restriction on how big x can be. Right? If x is 80, I can make this 1/4. Right? Theoretically, you could do that. So there is no bound on this. So x is between here and here. Now, this right here is very important. Because what if, I want you to think about this like what if question. What if I told you that it had to be like, we worked out a problem, we determined that this x had to be between 1 and 8. This would be a closed interval, wouldn't it? And we have a method for finding the absolute maximum and absolute minimum of a function on a closed interval. It's called the closed interval method. Right? So we would approach the problem differently if we were working with a closed interval. Because we don't have a closed interval, what we're going to have to do is do a table and figure out where this graph goes up and down. Arrows, and we're going to look for local max and local min. All right? So we'll do a problem where this happens. But for now, I want you to realize that we are on an open interval. All right, let's find the minimum of that function. So how do you find the minimum of that function? Local minimums. Take the derivative, set it to 0, right? All right, let's take derivative of this function. C prime of x equals, well, that derivative of 40x is pretty clean. That's 40. Bless you. And then remember, this is 660 over x. This is really x to the negative 1 there, right? And then you can do your little power rule there. So isn't that negative 660 over x squared? I'm trusting that you can do that derivative. And now we set it to 0. So what did I do to set that equal to 0? I got a common denominator. We've done that a couple of times now. You know, you had to set this to 0, but it's two different things. So you put them together, so you multiply x squared top and bottom here, and there it is put together. And now, you just set the top to 0. And I'll need some help on this on a calculator. You should get plus or minus some decimal. I moved the 660 over, I divided by 40, and I just killed off one of the zeros, so.
4.06.
4 point what?
06.
About 4.06 is what x should be.
Do we include the minus?
Okay, so now you go back and you look at, all right, our x's can only be bigger than 0, so we can chunk out the negative one. So we have a critical number here of 4.06, right? All right, this is not our answer. And students lose often on the problems like this that occur on the final. Students will lose credit right now because they'll box that as their answer, and they say they're done at this point. But all you've found is a critical number. You have not proven to anybody that that gives you a minimum, right? But that's our only critical number. Is it possible for the denominator to be 0? So we did need to look, was the derivative ever undefined or does not exist? And x is 0, right? But 0 is not in our domain.
Yeah.
So at x is 0, but not in the domain. Number line. I'm going to put 0 here. 4.06. 2 test points. What am I hoping to see here? What am I hoping to see when I do my test points? In terms of the graph, what am I hoping is going to happen?
A change in up and down.
Do I want it to go up and down, or do I want it to go down and up? I'm hoping to see down then up. Because if I see down then up, then I have found a local minimum, right? So I plug this in. I'm plugging 1, I'm plugging 10. Doesn't matter. And those are going where? First derivative, right? So we plug it in. You can plug it in here, or you can plug it into here without the 0. Either way, you're going to find down then up. Let's plug in 1.
40 minus 660.
660 over 1 is just 660. So 40 minus 660 is a negative number. So it's going to go down here. And if you plug in 10, go ahead and do it yourself. You'll see that it is positive.
4.06.
Agreed? So we have a local minimum at x equals 4.06, don't we? But remember, this said local, didn't it? Doesn't local only tell you what's happening locally? How do I know that this is the absolute minimum of this function? Think about the graph of this. What I know is that at 4.06, the graph has a local minimum, right? Like this? Okay. Why do I know that this graph doesn't like get lower over here? Well, to get lower, wouldn't it have to come back down? So if it came back down, I would have another change like up to down somewhere, right? But I don't. This graph only goes down. To the left of this, it goes down, which means it had to be above somewhere. And to the right, it goes up, so it can't ever come back down. So this is the absolute minimum of this function. Understand? Why what? Oh, maybe if I show you a different example. Let me graph a function for you. Okay, this right here is not the absolute minimum of this function, right? But if I looked at that, if I looked at my chart, it would be going down then up here, wouldn't it? Like my derivative would have said down then up. But see, this point over here is lower, isn't it?
Yes.
So if I would have continued my chart this way, I would have had another critical number, and it would have had to have been going up over here. See, like up, and then down, then back up.
Okay.
See, there would have to be another change somewhere else for it to do something, to get to a lower point. It would have to change back down.
So we would have another critical number then?
We would need, if we had another critical number, then we would have to be comparing the two answers. Pardon?
So we would have used a negative 4.6, but we were restricting it.
Because it's not in our domain, we don't even care. Even if there is a lower point over here, doesn't make sense. Because you're going to have, that would mean you have like a negative cost or something. Yeah, I mean, we don't know, but it's not relevant. It's not relevant to the actual physical word problem. Now, purely mathematical, without the fence and the farmer, then yes, you'd have to go look over there also. All right, shall we continue? We're not done. We just know that this is now a minimum. So we have a minimum cost here. So the minimum cost is when x equals 4.06, right? What is that cost? What is the cost at 4.06? So now you actually have to go into the original function before you took the derivative, which was 40 times x plus 3, well, I've lost it. What was it? 330 over, no, wait, no. 660 over x. You want to see what I'm doing there? Taking the original cost function, I'm plugging in the x value that gives me minimum, and I'm figuring out what that is. So who has that for me? 324.96? Okay. $324.96 will be the minimum cost to build this fence. Now, one addition, we've answered the question, haven't we? We've answered the question? Yes. What? Oh no. What was the question? How should I build it, right? This doesn't really tell me how to build it, it just tells me what the minimum cost is.
Yeah, that was the question. How much we construct?
So I would like to know the dimensions, right? Okay, so this gives me what the minimum cost is. To find the actual dimensions, what I know is that x has to be 4.06. Do I know what y is? Well, isn't y, didn't we already have it, that constraint equation, wasn't it? Wasn't it 20 over x? Y was 20 over x, wasn't it?
Yeah.
So if we do that 20 over 4.06, we get 4.92? Is that what you said?
Yeah.
4.92. All right? So 4.92. So let me go back over to this pen. There we go, like that. I want to build it so that this side right here is 4.92 feet. And I want to build it so that this side right here is 4.06 times 4 of them, right? So what's that, 16.24?
16.32.
16.24? If I build it that way, it will cost me $324.96. And there's no other way to build that pen at a cheaper cost. There's no other way to do it. That is the best way. Now, unfortunately, because I just made this problem up out of my head, the numbers turned out to be really close to 4 feet and 5 feet. But I was really hoping it would be something different, right? Because 4 by 5 seems reasonable to start the problem, right? Like 4 by 5, 4 times 5 is 20. Yeah, it works. It's almost a square. But it just kind of randomly happened that way. Had I changed the cost of any of those materials, then those numbers are going to change, right? If I made that wooden exotic fence $11 a foot, it would change what these values are. With me? So, Desmos? Okay, what was the original cost function? 40x plus what? 3? No. The one in terms of x. 660 over x. There's no graph because my window. I need my y-axis to go up to at least, let's go to 500. There's the graph of the cost function. So think about this real world, okay? Real world. Let's say you owned a fencing business, right? Or you had to do something like this. You don't need to know calculus. You need to know how to come up with the cost function, though. Because if you can come up with a cost function, all you have to do is go to something like Desmos and graph it. And if you graph it, you can tell right here that we have the lowest point on this graph is somewhere in here, right? So you're going to be wanting that dimension to be of x to be somewhere around 4, right? You don't want to build it, 8 feet long. You know what I'm saying? Like this could do it. And then even there's computer programs that'll find that lowest point very easily. Your graphing calculator can do it. I want to change the problem a little bit, okay? Does everyone see that we found the lowest point on that graph? Okay. Let's keep the chain at $5. And let's do the wood. Let's make this $12. All right? Then the way that would have changed our cost function is that our cost would have been, it was 5 times 8x plus 3y, plus now it would become 12 times 2y, right? That's what it would become. And that would become 40x plus, this would be 15y still, but now this would be 24y. And so this would now become 39y plus 40x. And now if I replace y with 20 over x, then we're going to get, what's that? 780 over x. So I'm going to graph that next to this one. 40x plus 780. Oh, this one gave me the lowest one. Okay? See? So the blue one is if we built it with different materials. What I'm trying to get you to see is that the lowest points, the x coordinates, right, are different now. So the way you build that fence would be different. We're at a point where I can't start a new problem. So I'm going to cut y'all loose, but I want you to see, just think about another example of this. Or how about I give this to you as a take-home? Yeah, here we go. Yes. That was brilliant. That was a brilliant idea I just had.
You're brilliant.
Okay, this might seem a little more...
Why don't we just talk about complex numbers? Show us the 1 plus 2.
You've got a company that's trying to connect building A to building B. This is a road. This is road, okay? And we're trying to connect building A and B with fiber optic cable. All right? And there's a rule that you cannot put fiber optic cable strung up over a road. I'm making this up. That if you're going to go across the road, you must go under the road. Okay, so you must dig and go underneath the road.
Okay.
Got it? Now, if you're going along the side of the road, you can put it up on poles. All right? And it's a lot cheaper to do it that way, right? So what I want to do is connect building A to B with fiber optic cable. The cost for going above ground is $2,200 per linear foot. Is that expensive? I'm sure these contractors charge a lot of money. Okay? $2,200?
I know, but like, imagine it's 50 feet away. It's almost $100,000.
Yeah.
I mean, it's a public project.
Okay, look, you want to change this? If y'all want, we can make it a different number. This is a government contract. So let me add another zero. Okay. This is a bundle of 200 fiber optic cables bundled into this very special casing. All right. So this is an expensive job. This isn't just one little cable that you're running, a little Cat 5 cable. All right. All right. Here we go. Yes. Cost underground is, let's go $4,300 per linear foot. It's expensive, man, I'm telling you. So this is building A, this is building B. The road is 40 feet wide. And the distance, the exact like horizontal distance across here from building A to building B is 300 feet. Make sense? Like if you were to go directly across the road and go straight down, that would be 300 feet. So
40 by 300.
think about how you could do this. My company could, let's think of the extreme cases of what my company could do. What would one extreme be?
If your budget was just wide open, let's just go A to B, straight subterranean all the way.
Okay, just dig from A to B, underground. That would be the shortest distance, right? That'd be the shortest distance. But it would be using the most expensive method the whole way. Maybe that's the best. Maybe it is. Maybe that is the best solution. But maybe it's not. So how do we know? We need to come up with a cost function and we need to analyze it. It may turn out that your minimum value is at an endpoint, but it may also turn out that your minimum value is somewhere in between. So what would the other extreme be? You don't want to bore completely underground the whole way. What would the other extreme be?
Go all the way along the outside of that.
Okay, go all the way down and then go across. That would be the minimum amount underground. But you got to go underground no matter what, right?
Yeah.
Okay, so I could go straight across and straight down. That would be the smallest underground section I could possibly have. So those are the two extremes. What would be some in the middle sort of situation? Excuse me.
Come down
You
somewhere.
could go straight from A underground and then build the.
Well, let's say there's something underground that you have to dodge. So you come down, 50 feet. You got to go at a diagonal, cut back across, go down.
Excuse me, I'm dying up here.
And then let's say like maybe there's a driveway.
How about I do that?
Overhead utilities. You have to go somewhere.
How about that right there?
There you go.
That would be some in the middle situation, right? Where you're doing some road, some underneath the road, and some along the side. This cost is definitely going to be less than the cost of doing just cable straight A to B in terms of, right? Or is it? See, that's the thing, you can't tell. The distance from A to B is shorter than this distance, right? You are doing less underground than you would be going from A to B, but then you have to follow it up with this part, right? Okay, that's everything you need. So the question here is this. Find the minimum cost for this project, right? And on top of that, tell me like exactly what point I need to aim at. So look at it this way. If I'm standing at A, right? One extreme would be to point, just go straight to B, right? The other extreme would be, instead of going across and down, why don't we go down and over? That would be the same as going across and down, right? So I could aim directly across the road, straight across and then go over, right? And then any variation of that would be here, right? Here and then here. So maybe we should just, I'm kind of giving you a hint here of how you can start to try and look at this, is like measuring the distance from here to here is calling that like X. So one extreme would be X is 0, right? The other extreme would be X is 300. And then something in between would be X is, 120. Somehow you should be able to base everything off of that. That should help. It's going to be an expensive project. So what do you say I give you all a week with that? Not because I think it's worthy of a week. Okay? It's because you've got some other things going on, and I want you to have an opportunity to maybe get together with other classmates and work on it together. Don't just go to the tutoring lab saying, hey, I got this problem. I need to, how do you do this? Like, I want you to try and figure this out. All right? I hope that today, these last two problems have kind of helped you believe a little bit that this has some value to it.